Thank you for the introduction. So our group receives research support from GE Healthcare. So as we've heard from the previous talks, dynamic contrast enhanced imaging allows us to do many amazing applications. Now for us, we're interested in detecting and characterizing lesions, and so 3D DCE really allows us to obtain these information for any imaging plane and at any time point. Now, of course, one challenge for 3D DCEs is that we have to acquire a huge amount of data within a fixed time window. And so what this means is that we cannot obtain both high spatial and high temporal resolution at the same time. However, our ultimate goal is really to capture the true contrast dynamics of DCE. And for this purpose, we actually don't need to achieve a high spatial temporal resolution scan for everything. And that's because DCE is not just anything. If you look at a DCE data set, it's very structured. I mean, we have these very fast blood flow dynamics, but they're also very sparse in the image domain. We have these patient-dependent kidney and liver dynamics, but they're also locally correlated. And we also have these background tissues that are essentially stationary over the time course and doesn't require much temporal resolution. And so in the following of the talk, I'll be presenting a new multi-scale low-rank reconstruction method that allows us to capture all these kinds of different structured dynamics, thereby providing us a better and more accurate reconstruction result. So how can we actually capture these dynamics? Well, many works uses the globally low-rank method that essentially allows us to capture the globally correlated dynamics very well. But the problem with this is that it is very sensitive to any kind of local dynamics, and you can get huge artifacts with this. So the low rank plus sparse method tries to fix this by capturing the local dynamics using a sparse matrix. Now, while this is suitable for some application, for example, angiography, in most cases, dynamics are not sparse. And so that's another problem. Now, if we want to capture the local dynamics specifically, we can use the locally low-rank method. But this only captures one particular type of correlation. And so you're clearly not using the data for its full extent, because we do have global correlation in our data set. So we have all these three methods. Each one is better at some area and worse at some other area. And so if you're a graduate student like me and you want to implement this for an application, you have to try all these and compare, and it's just terrible. And so what we're proposing is really a simple idea, right? Instead of implementing this separately for each application, we should really combine all these three methods. And instead of capturing only one scale of dynamics, we should be capturing all scales of dynamics. And that's because our data set has all kinds of scales of dynamics. And so instead of doing low rank plus sparse, you do low rank plus a smaller low rank and a smaller low rank and all the way to sparse. And intuitively, that allows us to capture, for example, the static tissue in the globally low rank component. The smaller low rank part allows us to capture the liver dynamics, the kidney dynamics. If you go all the way to the sparse level, that allows us to capture the blood vessel dynamics. If you apply it to a DCE dataset, this is exactly what happens. If you look at the 4x4 block sizes, it captures the blood vessel dynamics very well. If you go to the 16x16 block sizes, it captures the liver dynamics and also the heart dynamics. If you go all the way to the globally low-rank component, it even captures some of the respiratory motion. And so the multi-scale low-rank decomposition provides a very intuitive decomposition. But what this means is also that within reconstruction, you can basically ensure that this multi-scale low-rank decomposition would make sure that you won't lose these kinds of dynamics after the reconstruction. And here's how you actually perform the iterative reconstruction. So you first transform the K-space to image domain. And from this image, you construct these spatial temporal matrices with different block sizes. And now if you apply singular value threshold on these block matrices, that effectively just pick out the significant components for each scale and suppresses the incoherent artifact. If you put it back in, you get a cleaner image, and then you can go back to K-space again to enforce data consistency. Now, this update step is very intuitive and allows us to peel off the significant components for each scale iteratively. But it turns out it can also be formally derived using ISMRM. And moreover, the multiscale low rank is also a convex program, which means that it always converges to the right solution. And we also provide theoretically guided thresholds. And basically, for the multiscale low rank, for a particular block size, you would choose your threshold to be proportional to the square root of the block size. And so if you have 8 scales, instead of picking 8 thresholds, you would just pick 1 scaling factor. And so that's easy. One concern might be that the multiscale low rank is computationally very expensive compared to other low rank methods. But it turns out because we're decomposing each scale geometrically, the computation complexity also decreases geometrically. And so if you add everything together, it turns out it's only at most twice as more computationally intensive than other methods. So here are the comparison results. We've incorporated with compressed sensing with actually a VD-RAD undersampling, and also parallel imaging and respiratory soft gating. Now, if you look at these results at first sight, they actually look quite similar. But if you look closer, for example, this vessel, you'd start to see some differences. In particular, if you look at the early contrast phase, you'd see that the globally low rank result incorrectly enhanced this vessel. And that's because it's in trying to make everything to be correlated. Low rank plus sparse slightly enhances the vessel and also contains some artifact. Locally low rank has the right contrast but has more artifacts than other low rank methods. If you go to the multiscale low rank, it's the only method that provides the correct contrast and suppresses most of the artifacts. Here's another result showing an axial slice. First thing to note is that the locally low rank method is slightly more noisy. And that's because it's not using all the correlation that's available to exploit. And again, if you look at the vessel in the middle, you'd see that for globally low rank and low rank plus sparse, it has these spatial temporal aliasing. And that's because it cannot capture this scale of correlation. And only with multiscale low rank that you capture the correct contrast and also suppresses most of the artifacts. So what have we shown? So we've basically presented a really simple idea of combining all the methods into one reconstruction. And this allows us to capture the right dynamics at the right scale. And instead of doing just low rank plus sparse, this generalizes low rank plus sparse and incorporate locally low rank and also globally low rank. And we believe that this can be applied to many other dynamic imaging as well. And last, I just want to mention that none of the results would be possible without the Berkeley Advanced Reconstruction Toolbox that's implemented in C and CUDA and is available freely online. And thank you.